Okay, hi everybody. Welcome to our extra session where we are welcoming Ron Garcia to class. Yay, welcome Ron. And obviously this is an extra session and I do not have approval to be in my office. So now we are in my basement suite, which is why the internet is very choppy. So apologies to, for all of the technical snafus. But anyway, Ron is here, which I'm super excited about. And so Ron, as I was just saying, I didn't prepare a huge long intro for you. So quickly, tell us about Ron Garcia. From whence do you hail? Let's start with undergrad. Let's not go back to high school. That's too far. Tell us about undergrad.
I'd rather not remember high school. That was
No.
those dark days.
Same. So it's all gone for me. Yeah.
Yeah, exactly. So I went to undergrad at Notre Dame in Indiana, in the States. It's the home of the Fighting Irish. So it's an American helmet ball school.
Is that the one with the touchdown Jesus? Is that the place with
yeah, that's right, touchdown Jesus. Yeah. So I should explain the backstory there. So there's a large library called the Hesburgh Library, which is named after Theodore Hesburgh, who was the president and one of the main, he's one of the people who put Notre Dame on the map as a large university, and he is a really big deal. He was I think he co-founded the Peace Corps in the US, and there's a really iconic picture of him holding hands with Martin Luther King in prayer, like from back in the day. It's really amazing. I met him before he passed away. He was the real deal. Mm-hmm. So anyway, Hesburgh Library, his office was in the top of the Hesburgh Library. So it's kind of funny. But the library has this big mosaic of Jesus, because it's a Catholic university, and Jesus is like this, I am the way, yada, yada. Yeah. But if you're in the far side, but if you're in the far side of the stadium, you see him through the field goal uprights. And so he's like, touchdown. So he was touchdown Jesus.
Yeah, that's fantastic. Okay, so Notre Dame, and you did your undergrad in what program? In computing?
Oh, no, I was in electrical engineering. Oh, wow. So my stepdad was an electrical engineer. And when I was a kid, we used to like build computers together, and he was really creative. He could just build anything. Like he built like the timer lights for our garage doors and stuff like that. And so I was just like, I want to be like him when I grow up.
Yeah.
So I decided to study electrical engineering, and I sucked at it. I was terrible, not good. So I did the natural thing after undergrad, which was I went and got a master's in electrical engineering.
Yeah, of course. You keep going.
Yeah, so I just kept going, and then eventually I got the message, and I realized, oh, I do well in all the programming courses and terrible in the math courses. So I finally switched for my PhD.
Right. Nice.
Yeah. So
where did you do your PhD?
So I started my PhD at Notre Dame. I worked with a professor in EE, then I switched to CS. And then my professor, he told me one day, he's like, I'm leaving. I'm going to Indiana University. And I was like, take me with you? He's like, okay. So I switched schools, went to Indiana University with him, and that's where I got my PhD.
Oh, nice. And then was it straight to UBC after that?
Oh, not at all. Nothing straight. So after I got my PhD, I did a postdoc for 1 year at Rice University in Houston, Texas. And then I followed my partner to Pittsburgh, Pennsylvania, and did a postdoc at Carnegie Mellon. And then while I was there, I applied for the job at UBC and got it and came here.
Who were you working with at Carnegie? Do you, like, as a postdoc, just explain to everybody, you don't exactly have a supervisor, but you're sometimes like closely affiliated with somebody. So who was your close colleague in that context?
Right. So I specifically went to CMU to work with Frank Fenning. He's he's amazing. He's like my hero. And so he works on theorem proving and programming languages.
What is hero-ness for you? Like, what makes somebody Ron's hero? What is
okay. So
elevated to the status of hero for you?
So Frank walks on water. Like all of his students have this, like they basically all wear a "What would Frank do" bracelet. And I mean, he's brilliant, and he's capable of thinking so clearly, and you watch him work and you watch how he thinks about things and you think, wow, you think so clearly. And then you combine that with him being one of the most generous, gracious, and nice people that you've ever met, and like super well-rounded. Like he loves to play squash. Apparently he's really good at squash. I would never play him because he shows no mercy, but he also like loves hiking and loves cooking, and just a really wonderful human being. And so for me, he was a model of somebody who could be both at the top of their field and also always ready to reach down and pull people up. And that was just, for me, that's a hero.
Yeah, that's right. That's a good definition of a hero. Okay, so what was he working on?
Oh wow, so at the time, so Frank spends a lot of time, his PhD's in math and he works a lot in logic. And it turns out that a lot of work in programming languages has really close correspondences with logic, especially type systems are basically our logics. There's this concept that's typically called propositions as types, or the Curry-Howard it's like the Curry-Howard isomorphism or the Curry-Howard correspondence, which is basically saying that the way I think of it is logicians spent a lot of time trying to think, how do we have rigorous thoughts and describe them using symbols. And eventually programming languages people were like, oh, my programs are all crashing. How do I put annotations on them so that they stop crashing? And this weird connection happened where it turns out that the kinds of things that people were doing to build type systems for languages were exactly the same thing as people who were thinking about logical notions like entailment, or if-then statements, or and statements, or statements, that all of the formal symbol pushing systems that people were building correspond to types. So implication in logic is just a function type. Give me an A and I'll give you a B. And somebody'd say, if A is true, then B is true. And then and would be like a pair, like a compound data, where you'd say, well, if A is true and B is true, which is a way of saying I have a number and I have a Boolean. And so you can build up logical systems that way. And this was first discovered as an accident. And later people realized that, oh, well, if this works, then let's just go spelunking in the logic literature and figure out what cool stuff we can steal from them and stick in our programming languages. Right. So the Rust programming language uses, its type system is called substructural, which is like a fancy word for fancy. And basically what they did was they stole a lot of ideas from logicians who are trying to think about resources, basically. How do we talk about I have a thing and the thing is ephemeral, it's not true forever, but it's true for a time and then it goes away. Right. And so they figured out that you could use that to capture memory allocation. And how do you make sure that you free your data and without having to explicitly write it in?
Yeah, almost like sort of a passive garbage collection kind of feeling.
Yeah, but it's not exactly, but it's not even garbage collection. It's just with garbage. Okay, so I should say it is a form of garbage collection. It's a form of memory reclamation. Yeah. But it doesn't involve having to trace your program. You don't need a garbage collector in the background tracing your program.
It's like a natural attrition of the set, like a degrading state, as opposed to some sort of reference hunting or something like that.
Yeah, it's like the way you write your program and the way the system type checks it, it can tell exactly when you can never look at your code again and just add a piece of data and just deallocates it, which is really cool. And makes it a lot easier to write low-level OS code that doesn't have double freeze or seg, other things that cause seg faults, basically.
Right. And so is that how you got into gradual typing? Is this because this is what you kind of have introduced and what you do at this point? So
right.
Was that journey through to that?
So that was part of the journey, is what I would say, because at least at the time, if not now, CMU, where I was basically one of the PL meccas. Basically, it's just a place where a bunch of the most brilliant and rigorous programming language theorists were and are still today. And so it was almost like getting a second PhD to go there and just learn from them. And I was not I did my PhD was about C++ metaprogramming, basically. So I was just like, so I should say Indiana University, where I did my PhD, is like a scheme hotbed. So like Racket, Matthias Felleisen, who started the Racket project, he did his PhD at Indiana. And then so there's this sort of like loop where his supervisor and one of his students were on my PhD committee, because one of his former students like went back to Indiana. So I got really into macros and like scheme macros and Racket macros, and that's a form of metaprogramming. But I'd been in a group that was doing a lot of high performance computing, and we were using C++ templates to do just crazy things. So there was this really nice two ways of thinking about writing programs that write programs. One of them using C++ as type system, and the other was using schemes macros that really influenced this research group that moved from Notre Dame. And so I was into types because I was into metaprogramming and I wanted to write fast code. And then I really learned about types when I went to CMU. But I was always into Scheme. So I was like, my two favorite languages were C++ and Scheme, which is basically Racket. And so I always go back and forth. Like, I really like the dynamism of a dynamic language, but I like the rigor of types as well. But I'm kind of persnickety, and so I wanted both. I wanted my cake and I wanted to eat it too. And so the question I always asked myself was, does this even make sense to combine static and dynamic type checking? And it's like that curiosity is what's driven my research.
Nice. Oh, fantastic. So, and what, so I mean, I feel like I could talk to you all day about what you're working on now, what interesting projects you have going, all these kinds of things. But let's just return to context. So this is 310, obviously, and we most recently have been talking about design patterns. We've had so many excellent conversations about how design patterns look differently in different kinds of languages, and our design patterns really just workarounds for language issues or whatever. But the one that so we can get into all those things. The one that we most recently talked about was the visitor pattern. And so just for some context for everybody here, last year when I was doing my visitor pattern lecture, I had to like phone a friend, and the friend was Ron. And I had to say, like, how do I make this evaluator work if it has to return different things? And so Ron helped walk me through the whole generics of the visitor pattern, and then we got into a long conversation about the visitor pattern. And so I thought it would be fun for everybody to hear Ron's thoughts. But so Ron, visitor pattern. One of the things that people asked about immediately was like, is this a problem of Java, or is it why, and this, I think you and I had talked about this too, why is multiple dispatch so hard? Why do we need the visitor pattern at all? Why can't we just put a whole bunch of types in and have it resolved? So what's going on?
Oh, it's a great question, and there's a lot of richness in it, right? I would say I'll try and keep it to the visitor pattern, just because that's the question you're asking. So one of the
it's completely fine. Like I think people are fine with a broad answer. So
okay,
cut loose, yeah.
Yeah, so like so I teach 311 and I've taught 110, and in both of those we use these data definitions where you sort of build these little closed worlds where you'd say like an expression, like in our little programming languages, you make a little arithmetic expression language, and you'd say an expression is either a number or it's like add of two expressions, or it's minus of two expressions. And so you create this little world, and that world is closed, which means those are the only expressions that ever exist, and I can just lay that down. And now when I write programs, I'll write a function that takes an expression, and I only have to check three things. I say it's either a number, or I'm adding two things together, or I'm subtracting two things, and then you just recur. So that's very closely tied to functional programming, basically. I worry about saying things like functional programming because you can easily think of it as a language, like, oh, like this language is functional programming and this language is not. And it's more about style. Style is more important than your language. So a language like Smalltalk, just to kind of go with a language that was really designed to be pure OO, and Java was heavily influenced by Smalltalk. So I think it's fair to put those two together. But those languages, rather than writing a data definition, where you say, I'm going to create a world and then I'm going to completely populate it, instead is more designed to favor creating open worlds instead of closed worlds. So your class hierarchies are these open worlds where you'd say, if you're going to do what I'd call pure OO programming in Java, the pure OO style is to say, I'm going to create an abstract class. And my abstract class might be expression, as you would probably show them. And then you'd say, and then from there, I can create subclasses. So I could create a number class, which is an expression, and that's a concrete class. And then I have a sub, which is another subclass. And then I have an add, which is another subclass. So at this point, we have these two data structures, which are very similar in both languages. You've got your closed world over here, and you've got your closed world in like Racket for our purposes, and then you've got your open world in Java. And the difference has to do with what happens when you change your program.
Right.
Where are the pain points and where are not the pain points? So I was pointing a student to this before, and this is often called the expression problem. And it's a joke because it's like, basically, how do I extend my language with my interpreter with expressions? So it's kind of these two things are, and also how do I express change?
Right.
So in the let's say one thing is like, suppose I want to add more features to my language. So now I want to add division. Like, how do you add division to your typical Java program? You add a new file. You introduce a new file with division. You create a class. You don't touch anything else in the system. And then you write your methods. And so you can overload them. Like if you had a method for evaluate, a method for type check, then you just add purely. And so this is fits what you'd call the open closed principle, trying to keep your code open to extension, but closed to modification so that it's kind of clean. On the other hand, suppose I want to add a new piece of functionality. It's like, I've got type check, I've got evaluate, now I want pretty print.
Right.
In the Racket world, what I do is I have my data definition at the top. I've got a type check function. I've got an evaluate function. Now I want to add a pretty print function. I just also can create another file, just write the function. It refers to the open things. And it's beautiful. Like I can add functions over here in the Racket world, and I can easily add new data over here in the Java world. The tension comes when you decide, what if I want to add new data in my Racket program? And alternatively, what if I want to add new functions in my Java program?
Right.
So both of those are in tension. In both of those cases, if I want to add more data over here, then I have to modify my data definition, which means I have to modify every function that I already wrote. In the Java world, if I've got a class hierarchy with methods and I want to add a new function, then I have to modify my abstract class, add a new method, and then I have to jump around and modify everything. So it's not uncommon. So there's a great computer scientist, Alan Perlis. He won the Turing Award, and he always said, it's better to have like 10 functions that operate on 10 functions that operate on 10 data types rather than 100 functions that operate on 100 data types, roughly speaking, was his saying, which was like, it's nice to have a common data source and then add more functionality. And so if your goal is to structure your code that way, then you want a language where adding more functionality is the smooth path, right? And the sort of data type version, like in Bracket, kind of fits that. And in essence, the visitor pattern in Java is the way of doing that thing that one would do in Racket naturally, but suited to Java.
Right.
But what can get forgotten is sometimes you want to create an open world system. And when you want it, where you want to be able to add new functionality, and this is really common in like, if you have APIs in the world and things like that, and you want some dynamism, a language like Racket may have to deal with that. And if you're building a large system, you may run into a need for design patterns over in the Racket world that can support adding functionality.
Right. And
so there you need to end up basically using first-class functions to simulate class hierarchies. So, so basically, it's a real challenge to find to create one language that makes everything easy. I don't think that's ever going to be done, but we're getting better. Like Scala brings a lot of those ideas from over here into a kind of Java-like world, so you can have both kind of coexisting. Right. And vice versa, like OCaml, Objective-Caml in the functional world does the same thing. It brings objects into the functional world. So that's kind of a broader view of what's going on with the visitor pattern, to say that right. It's not that every program that you write is going to have some sort of software architecture to it. And the visitor pattern is one means of achieving a certain very useful kind of software architecture that is not the path of least resistance in an object-based language.
But do you think that so I think that the natural next question is, okay, it makes complete sense to want to separate out the functions that the visitation would encompass, like a pretty print walk or a evaluate walk or a type check walk or whichever walk. But why do we need the there and back? So we know why we need it. We know it's because Java is a single dispatch language. Are all languages single dispatch? Does Java have to be single dispatch? I remember in the 90s that there were people writing multiple dispatch papers at UPSLA, like trying to make it work in Java, and somehow never caught on or never got integrated into the core. What is the challenge? What's happening?
Okay, so let me kind of step back a second, and this one's tricky if your students are primarily know Java, so I'll try and explain it somewhat generically, because I have to kind of go back to the Racket world.
They know Racket, TypeScript, Java. They're polyglots at this point.
Perfect. Okay. Yeah. So especially if you took 110, in the middle of the course, there's this point where you talk about abstraction, where you say, oh, we see common patterns, and we want to capture the pattern and then write just enough code to capture the difference between the common pattern. So like you take two functions and you realize like, oh, the only difference between these two functions is this one thing. So let me remove that thing, introduce some form of parameter, like either a variable, and then write a function that just takes that argument and then goes. And then you can push this further in Racket by saying like, oh, you can do that with functionality because you can pass in a function. So at some point, it kind of gets pushed to a point of, especially it's a point of difficulty for students the first time they program, especially, is what's called an abstract fold function, where you say, if I have a data type in Racket, I can define like almost a universal function that takes functionality and implements whatever. And that's called a fold function. And so that fold function takes some pieces of data and some pieces of functionality and then just like, bam, like implements the thing you want. So if you think about what's happening there is I'm passing in callbacks or procedures or objects. Yeah, like and then the body of the abstract fold function at certain spots uses those callbacks and passes in data. Sure. That is exactly the same double dispatch as happens in the visitor pattern. Like it's like I've written code to show you that, oh, if you take all the arguments that you passed in, collect them into one object and pass just the one object in, and then the body of the fold function selects your methods and calls back. Yeah. It is literally the visitor pattern. Yeah. So what's happening there with that version of double dispatch is you've captured an abstract pattern. The visitor, your class hierarchy contains the fold function, and it just happens to be called visit instead of fold. Right. And it's scattered across all of your objects, which makes it harder to realize that you're writing one function that happens to be called visitor and dispatches on each thing. And then each of your subclasses of visitor is your particular instance of calling fold. So from a dynamic point of view, there's something essential about this idea of double dispatch for the visitor pattern, because what you've done is you've created a template for doing work which has holes in it, and then you instantiate them. Right. And whether you do it using template instantiation like in C++, or do it using virtual method calls in Java, or do it using lambdas in Racket, those are all the same.
Mhm.
So there's another answer to your question, though, which I think is an interesting one, which is there was a bunch of research that was done on languages that supported multiple dispatch, where you could have a function that takes like 5 different things and then looks and sees what are the 5 different things, and then do something different depending on them. Like
intuitively, it works, right? Like we can reason about it. If we look at a parameter list, we can be like, that's the best fit, right? Like there's the receiver, and then here's the parameter types, and then like you can kind of imagine which one the developer means. So why is it difficult for a programming language to make that decision?
So I don't know that I could give a definitive answer to this, but I've seen in many different circumstances the same question come up as, oh, we can get it to make a decision based on one spot. Why don't we get it to make a decision on multiple spots?
Yeah.
And hilarity always ensues. And I think what part of the reason the hilarity always ensues is that when you have a single point of decision, there's not a lot of, there's something to be said for having constraint in language design. In the early days, people get excited about more expressive power, more expressive power, more expressive power. Like I want my Perl, I want my APL, these languages that are super powerful and also very malleable. So especially in the OO world, malleability was a really big topic. I've been reading a lot about the self-programming language, which kind of like took small talk and turned it into its essence. It's beautiful. But the goal was to make a language that was utterly malleable, where you could just change everything all the time. And so there ends up
the author. So Dave, do you know Dave Unger? He's
well,
exactly like that. He's such a cool character.
Yeah, he's fascinating. I had the privilege of hearing him talk about self in a reading group that was reading his paper, and he gave us a lot of like the inside scoop of what he was thinking about, and it was really cool. I've never met him in person, but I've seen him from afar, but I've never actually like talked to him. And so there was this interest in like being able to empower people by adding expressive power, but making it a certain aesthetic of simplicity, but with unbelievable ability to change things. And many of our scripting languages have this sort of thing on the side too. You have reflection. It's like, oh, I can dive underneath and like replace all of your ones so that whenever you write 1, it actually does 2 or something like that. And there's something very intoxicating about that kind of power. But it has cost. And there's multiple costs, and one of them is that if you have a constrained language, then it constrains the design space and what could possibly make sense to do at each point. And so when you add a little bit more flexibility and generality, there's not always an obvious decision what to do. So having multiple dispatch can lead to many possible language designs, each of which will be good for some programs and not for others. And so this happens in like the Haskell programming language has this feature called type classes, and it dispatches, it's basically overloading on steroids, static overloading on steroids. But then they started thinking, well, why don't we do multiple position type classes with multiple overloading? And falls into the Turing tar pit. The type system becomes undecidable kind of instantly. And so you have to be very careful. So the 2 things that happen are, one, as you add expressive power, it becomes harder for me to predict the behavior of a program by looking at one small spot because of the many possible things it could do. And our brains are small, and you've got the rule of 7 plus or minus 2. And then the design space gets so big that trying to figure out what will work well gets harder. And I think we'll probably keep trying. Every once in a while, someone will be like, yeah, like, I mean, there is a language called multi-Java, which really works on symmetric multi-argument dispatch.
Was that the one by Guy Steele or no?
No, that was Fortress was Guy Steele. Multi-Java was Craig Chambers.
Yeah, okay, Craig.
Yeah, and so he was Jonathan Aldrich's supervisor.
Yeah.
So, but it never really took off, I guess. And part of it is it's really challenging to support modular software design and multi-method dispatch simultaneously. And that was what he was working on.
That is, yeah, that's so interesting. So, I mean, I can understand theoretically why, but I guess as somebody who's like imagined what I would like, and I think you and I had this long conversation and I asked you a whole bunch of like, but why can't you just like,
Right.
but why can't you just have a lookup table, or why can't you just express preferences in the thing, or like why can't you say you can only do it within a certain range and then like cut it off or something like that? Like why can't there be some sort of compromised version of this so that we don't
Yeah.
have to write an accept method into every single class or whatever?
Yeah. It seems like a lot of software design or language design, well, language design is software design, same difference. A
Yeah.
lot of design, the beauty of designs are when everything falls together, like these sweet spots.
Yeah.
And like even like Smalltalk makes believe that numbers are objects and that in principle you could actually like overload. You could just like rewrite the implementation of plus so that your numbers do something different. But nobody does that, and the
Yeah.
runtime won't let you. And Self had the same thing. They were like, yeah, there's one's just a name of a method slot in like some Uber method. But we were worried that people would do crazy things, so we left it out of the language. And so finding the right, given this large design space and the wide number of things that one can do and the sort of limitations of the human mind, often, and human capacity, which decreases as our computing power gets higher, finding really nice compromises that create the illusion of the perfect abstraction far enough seems to always be the thing that we do. And then at some point, there's tension arises when you finally push the edge of that abstraction and the illusion starts to really start bothering you. And I think that the event horizon of multi-method dispatch, people were never able to get it far enough out that everyone would be stay within the comfort zone, I think. And it possibly is just because these were research languages, and the people who like research languages are people who like to push. And
So is the problem the combinations? Like, let's just get down to the nitty gritty of what makes it hard.
oh yeah,
Like, is it that it's the combinations of things, and like how do you prioritize which combo you would be picking? Is that basically the problem?
I would say, yeah. So I would say it's a combination of how do you choose the combinations, but even more, what are the defaults? Because if you have 5 slots and you want to choose based on 5, in principle, there's 2 to the 5 things, or whatever. I don't do math, whatever. There's something to the 5 possible checks, but you're not going to implement all of those, right? And you want a language that allows you that expects the quote unquote natural thing for the set of developers that use it, so that to them it seems seamless, like, yeah, obviously I'm only going to implement these 3 and then it'll just do the right thing for everything else. And so getting a language design to be able to fill in the gaps that you don't want to write yourself is one of the great challenges of programming, is like doing the right thing that's left unsaid is hard. And that's like we were learning about type inference in 3.11, where it's like, I want to leave out all my types and I want the program to type check. And then you're like, there are some languages where if you pick your battles correctly, you end up with something beautiful. And then if you try to generalize a little bit, it all falls over. And so like there's this, yesterday there was a plenary lecture on Algol 60, which as Turing Award winner Tony Hoare says, is like the language that is, it was way better than all of its predecessors and most of its successors. And basically Algol introduced most of the features that are in any language we program in now. But then 8 years later, they came out with Algol 68, and they're like, let's add more stuff in. And it was, let's generalize all the features of Algol 60 in ways that it didn't. It was limited because people were like not sure how to make things work. And what happened with 68 was a total disaster because it was too general and like utterly unusable. And 60 was a beautiful design that just happened to like everything held together. So it's kind of that same
Mhm.
phenomenon, but at a language level. Sorry, I'm going on,
No,
but
no.
this is really thinking about language design is it's an art, it's a craft, it's
Yeah.
a thing that people learn by looking at what came before, and every once in a while you have a Michelangelo who comes up with something you've never seen. People build on it. You know, you have schools of thought, you have like rivalries, and it's all about design, aesthetic, and utility as well, of course.
Yeah, yeah. So, who are the Michelangelos of programming language design at the moment?
I mean, the Michelangelo, the singular Michelangelo is Guy Steele,
Yeah,
as far as I'm concerned. You know,
yeah.
don't at me. Guy Steele is the most brilliant programming languages person I've ever thought of. Now, I should note, people, if they go look at Guy Steele, they'd be like, oh, so it's the guy who invented Scheme as his master's thesis. And I'm like, yes, that's true, but that was the beginning
Mhm.
of what Guy Steele
Yeah.
did and does.
Mhm.
He's just got this amazing mind for thinking about languages and thinking very broadly. And he's also like, he's a square dance caller. And I got to meet him once when I was a graduate student, and he talked about how, you know, you can really think of square dance calling as a language. Like it actually has like a syntax and semantics to it, and he can really bring this aesthetic. And he's the single person who's probably been involved on the most standards committees ever.
Mhm.
Like he worked on JavaScript, he worked on Java. His role in Java was basically to look at James Gosling's standard and say, can we change this feature? Because then I can delete like 20 pages of your standard. And he's like,
Right.
yeah, you should do that. So
You go for that. Thanks. Yeah.
yeah, so I sort of think of him as like a high performance engine producer who's just has the
Mhm.
mind for making everything stick together.
Yeah. So for context, for those watching the video, we actually just chatted with Dick Gabriel, who is Guy Steele's.
Oh yeah, that's right.
And
Yeah,
I had the privilege of hanging out in Australia for weeks with both of them, so,
awesome,
which was
awesome.
a lot of
I'm
fun.
jealous.
Yeah, it was great. It was actually Guy Steele's wife who identified that I had celiac, probably. It was formative for me, for so
Okay.
many reasons. But yeah, so and now he's working on Fortress, which you mentioned briefly earlier. So
Mhm.
does Fortress have multiple dispatch? Is it,
I believe
we
Fortress
finally
does.
getting, are we getting? Yeah, finally we're getting
Yeah,
it.
so actually, no, now that you mention it, so I guess the story of Fortress is, for background, years ago, back when people didn't invent new languages, like for years, it was like, you know, nobody got fired for using C++. And then like now there's this cornucopia of languages, which just didn't happen when I was young. And so there was a contest by the US government to kind of create a new language and new hardware for doing like scientific computing. And
Mhm.
so Guy Steele was working at Sun, and they started working on a hardware problem, and they started building this Fortress language, which was an extension of Java and combining the mathematical ideas of Fortran with like modern GUI technology and stuff. And so so one of Guy Steele's employees was Sukyoung Ryu, who's a professor at KAIST in Korea now, and actually a friend. And Sukyoung has always been into type systems and stuff. And recently, Guy, her and her students have been publishing papers on how to make multi-method dispatch
Mhm.
work better. Sun, unfortunately, didn't get past the last round of funding for this project from the US government. And so they just canned the project. So it's sort of like a labor of love for Guy and Sukyoung at this point, but they keep pushing on it and making progress.
Nice,
So that
fantastic.
was a long answer of yes,
Yeah.
it has multi-method dispatch.
Hilarious. I realize that we're using up lots of time, but I just wanted to ask, just going back to something that you said a little
Oh,
while ago,
yeah.
which is there might be different patterns that you would use if you were employing a functional approach. And this is something that people ask about a lot. Like when we talk about design patterns in our class, we're talking about object-oriented design patterns. We talked about REST a little bit, which has its own set of principles of design. Of
Mhm.
course, there are architectural design patterns, there are design patterns. So but our students are really familiar with functional programming because they went through Racket.
Mhm.
What are some examples that, like the recipes that are in 110 are not design patterns, right? They're like process patterns almost. Um,
Right, right.
or
So
like the pattern language kind of thing that Alexander would refer to. That's more what they are.
mhm.
But what are the kind of structural or behavioral or whatever design patterns that exist in the functional world? Because I actually don't program in the functional world, so I have never
Right.
encountered them.
Yeah, so there's a bunch. but so there's this really sort of problematic facet of a lot of the functional programming community is an obsession with mathematics and archaic terminology, which I think I get it because I'm in the community and I understand that much of the original idea of functional languages was being inspired by mathematics, and it's not the same thing as mathematics, but the idea was like, wouldn't it be nice if I could write down a program and it was meaningful sort of mathematically, but it also ran, and like blurring the divide between the two. And what's ended up happening is people have found that you can sort of transport and transform ideas from the mathematics world into programming idioms that end up being really powerful. Because basically a lot of higher mathematics is about building abstractions. It doesn't look like it when, I took some math classes when I was a PhD student, and it was all like, what the hell is going on here? Like, none of this makes sense to me. I'm a coder, leave me alone.
Right.
And it was only like years later after, you bash your head against a glass, wall for a while, and then like you get like a little crack and like, oh, I made progress. And so this thing that people talk about all the time. So in 3.11, we spent time using something that I called an effect abstraction, which most programming languages people would call a monad. And a monad is technically a monad is a mathematical structure from an archaic field of mathematics called category theory. But what happened was a theoretical programming languages person who's trying to figure out how to build mathematical models of languages kept running into this problem that like, you're like, oh, I want to model a language that has like, mutable boxes, like, stateful language. And you're like, okay, so I do all this work. And then you're like, oh, and now I want to add like jumps and go to, and you're like, oh, I have to start over from scratch and like do all this stuff. And like, oh, and now you want to add like input and output. And you're like, oh man, it's like, and now I want exceptions. You're like, what the hell? Like every time I add a feature, I have to go back and start from scratch and write the whole thing again.
Yeah.
So this was a real problem for the people who were building mathematical models. And at the same time, there were people who are like writing interpreters, and they're like, oh, like you can look at somebody's mathematical model, and because our programming language code looks a lot like math, you can almost just write down the math and it just runs, which is like one of the beauties of functional languages. Yeah. So there are people who figured out like, so Eugenio Moji, this person figured out, he's like, oh, like I can steal this idea and it gives me the ability to say, I'm going to have a language, it's going to have some sort of effects in it, and I'm not going to tell you what they are, and then I will add them as a separate module. So I get sort of an open-close principle of effects. And Phil Wadler, who's another researcher who liked definitional interpreters, he's like, wait a minute, I can like implement that. And he's like, and then you come up with this design pattern for how do I write programs that abstract away a lot of really complex details so that I can add new mechanisms to my program one at a time. Like it's almost like I'm working in a really restricted language, and then every once in a while I want a superpower, and you're like, I'll just add the superpower over here, and then I don't have to modify my code. I don't have to rewrite it from scratch, but I can just use my superpower in this one spot in the program.
Right.
And that's one of the really popular design patterns in programming languages. And the problem with it, and part of the reason people don't know about it, is it's not typically explained that way. As it's a way of modularizing your code with respect to behaviors. Right. People are more like, well, let me tell you about category theory. Like there's like functors and natural transformations, and you're like, how did we end up like, wait, did I walk in the wrong room or something like that? So there's barriers to entry to a lot of the design patterns in functional languages. And there's a few more that have this feature, like there's something called lenses, which is another way of thinking about, a lot of times you want to have a program where you project data out of it, right? It's almost like a database where you take a view and then you want to transform things. Yeah. And then you have like the view update problem, which is where like, I've got a view and I want to modify the view. I want to look at this thing, modify this, and I want the other stuff to change.
Yes.
And, every sufficiently large software system is going to run into this problem.
Yeah.
So, Benjamin Pierce, who's a famous PL person, and his student at the time, who's now a famous PL researcher, who works on like domain-specific languages for networks, like for distributed networks, like for routers and things like that. Nate Foster, they did this work on what are called bidirectional transformations, which later became called lenses, which is basically, can we build a language of components that allow us to build up programs that have that property where, yeah, I've got a program that runs this way. I have the ability to take views. And then it's just like, boop, like now I have the view, like it solves small cases of the view update problem. And this is a really, for people who now program in like Haskell in industry, they often end up using this archaic seeming thing called lenses, which is just like, how do I solve this projection transformation problem? And if they called it like if they called it projection transformation thingy, people would be like, yeah, that's the thing I need. But so unfortunately, there's a lot more lexicon transfer that needs to happen, where being able to explain things in terms of the needs of the people as opposed to the mathematical inspiration is lacking in that community.
Yeah, I mean, object orientation went through a pivotal moment with that, right? When the Gang of Four got together and they started curating all of these things. They took you know, a lot of work that people had already done, but they did, you know, and it's a controversial thing that they did actually. And Richard was talking about that, but then, but also they did kind of bring it into a pragmatic lingo that everybody could kind of action. Like it became something that could be kind of traded on like a currency. So
yeah, like it's almost like I think of it as almost like so I used to love, this is going to be really I worry about the cultural implications of this, but I used to love like Kung Fu theater when I was a kid. Like you'd always watch these martial arts shows when I was little, and it would always be like there was some particular like school of thought and another particular school of thought, and it's like, you know, do you know the burning hand like move and stuff like that? And they would like these like,
and like, yeah, but we call it the burning foot or whatever. And you're like, oh.
Yeah. And so they'd hone these disciplines, and the same thing happens in programming, and we don't always have a common lexicon, and we don't even have names for things. It's just like the experts just know, and they do it without thinking, and we never identify it.
Is that we haven't drawn boundaries around so much of the stuff that we do actually. So that curatorial step was actually key, because it sort of like names pointed at things and said, these are things that exist. Yeah.
Exactly.
Yeah.
So I think you've pinpointed something that I think is really vital for communities of development. Is this curation is important, but I also think have curation with an eye towards accessibility and invitation. Like your goal is to bring people into the community and not use it as a gatekeeping mechanism. Like, well, I've seen there were some really controversial
or something.
Oh, what's that?
Like bravado or whatever, like sort of like,
yeah, or like, you're not a real functional programmer.
Yeah, that's right.
If you don't use 5 monads and an algebraic effect in each of your programs or something like that. And sadly, I've seen advertising for conferences that do stuff like that, and it's really unfortunate. But it's not everyone.
Yeah, it doesn't get any EDI points, that's for sure.
Yeah, exactly. I think that's important.
Yeah, I think it is, actually. It is important. And this brings me to, so we're drawing to a close. I've taken up a lot of your time. I'm so sorry. Last question.
Oh, this has been fun.
Yeah. So this is my absolute last question, though, I promise. And it's just a minor question, but how do you see the future of education for software engineering and programming languages? I mean, I have a lot of thoughts about the fact that these are very sort of like related disciplines, right? Like we have 2 different courses. We have 311 and 310. And I don't know, like the fact that they're separate, I mean, it's a useful decomposition, but you and I talk a lot about the intersection between our fields, so much so that I almost don't see a difference in our fields.
Right.
So how do you think we should be moving forward with teaching all this stuff?
It's hard. I don't know that there's easy answers, and I think there's multiple reasons for that. And I even see it like within the department, among the students, among the faculty, is that we all come from, like, it's like we all grew up in different monasteries and learned different moves. And we come together and we're here with the collective goal of educating the students of the future. It's basically we've created our own new school, right? I mean, literally, that's what we do.
Yeah.
And so I guess as a useful background is like one thing that I love about UBC compared to other places from a research point of view is that software engineering and programming languages were like this. And there's other schools where they're like completely in different buildings, literally.
Yeah.
And there are some differences, like within the community, within either of these communities, there's wide differences. And then across communities, there's a lot of differences in both like aesthetics and goals and background. And like, so for instance, I think in programming languages, like the human aspect in some parts of the programming language community was put to the side, and more focus was on mathematical perfection.
Right.
And some of that is changing now. There's really people who are bringing humanity into their theoretical computing work. There already was, but there was sort of disparate, that there were people who are more on the humanity side and there are people who are more on the formal side, and now they're really coming together, which is great. And then software engineering, often because the issues that drive a lot of the thinking there was scale, like how am I going to get Google to be able to do this thing, whereas over here we're like, how do we get it perfect? And so when it's like, yeah, you could do it perfect, but it will take a week for all the test cases to run and verify your code, then you have a problem. And so there are theorists who've kind of moved into industry who realize we can't try to do the perfect thing. It may be decidable, but decidable isn't good enough when it means the heat death of the universe before you solve the problem. It's like, yeah, that's a finite amount of time. So what if the sun has boiled the earth? Who cares? So, yeah. But to get back to your question, I think there's something to be said for bringing many different perspectives to students, because it's dangerous if we weave a story that everything is airtight, that knowledge is invariant and perfect and done, and we are just going to feed it to you and you will know it and it will constantly accrete. It will only grow. Knowledge is always contingent on humans, communities, tribes, and especially for computer scientists, it's really painful to start hearing that story. Like, you're saying I'm no better than anthropology? I'm like, yeah, you're no better than anthropology. It's just our stuff runs on computers. But ultimately, our knowledge is, the way we organize information is ultimately about the communities. And teaching students, here's a discipline for understanding something, and don't take it as writ in stone. Like, there is no single logic. All of logic is contingent on axioms at the beginning of time. There's no single programming language. DNA can do computation, which changes how you do your architecture. The rise of quantum computing is going to change how you think about how to build computations and compose them. And so, but you have to start somewhere. So we have to say, like, here's the Bohr model of computing, and here's the Bohr model of software engineering. And we need to prepare you to synthesize lots of points of view and grow your own and grow as a person over time. And I think our ultimate challenge is, how do we build self-growing people who have enough background and enough context to understand their place in the world and the history, present, and desired trajectory of the field. I think that's the ultimate goal. But I think part of that is breaking down some notions of permanence of ideas and putting forward the idea that ideas are always filtered through minds of humans.
I mean, that's such a valuable point, and it is such an unsettling thing for students to hear, right? Because at some point, like, if there's no ground truth, then how do you write a final exam? Like, how do you know that you're ever right or that you're ever wrong? And it feels groundless, I think, to students.
Yes.
Right?
It does.
Yeah.
And it feels like, this is unfair. You told me things were this way. And then you swept the carpet out from under my feet the next year. And it's like, we can't get you there in one step. We have to scaffold.
Yeah.
But I don't think we do as good a job as we could in telegraphing that that's where things are going.
Right, because it's about these useful models, right? Like, all the models in physics, they're not correct. They're just useful, right? For now. And I think that's what each of our courses is as well. They're kind of these sequence of useful models, useful ways of thinking about different problems so that you can deal with them at all, as opposed to, here's the truth of programming languages. This is the truth of type inference. Like, there's no truth of type inference. There's no truth of design principles. Definitely no truth of design principles.
Yeah.
So yeah, I think this concept of just like opportunistic learning, that you're kind of able to just mine the ground of what people know. But you're right. I think we don't do a great job of giving students that mindset that this is, and it goes beyond just growth mindset, right? It's like this useful kind of this little trick where you're just saying, can you mine what I'm saying for some sort of tactic or strategy for thinking about your world, basically.
Yeah, or recognizing that science is a social construct. That was a very painful and long running problem for me to come to understand, that ultimately science is about the societies that hold the science. And that doesn't mean anything goes. So that's the tricky part, is balancing. It's like, oh, it's not that the earth is flat now because, because physics is fake, because physics is a lie, because, physicists don't actually know what gravity is, which is true. They have no idea what gravity is. They build these models, and their models work until they don't.
Mostly.
Which means
yeah, that's right.
they're useful as long as you're not near a black hole, which makes them seem like truth, but they're not, because they don't work in black holes. So it's easy to think that you have facts on your side, and that when you have facts on your side, you don't have to worry about human interpretation. But that's an abstraction, and it's one that's often harmful.
Yeah. Well, Ron, what a wonderful point to end on. That was great. I could talk to you about that for hours and hours. That might be a sequel. Maybe we can come back next semester and keep chatting. But this has been really wonderful. Thank you for visiting us.
Yeah, well, thanks for having me. I hope it was useful.
Stop recording, because it's always fun to stick around. But thank you so much. And I know I'm speaking on behalf of everybody here when I say thank you for joining us.
Oh, you're welcome.